Hi again, Cauchy, and thanks for checking out our second video for the week. I promise this one's going to be a little bit shorter. I know I'm really working hard on trying to get these down to 15 minutes, but it's hard to get that in there. So today we're going to talk about the formal definition of a limit, sometimes called the Cauchy definition of a limit, sometimes called epsilon delta proof of a limit. So it's got a few different names. All basically means the same thing. It just kind of depends on what your textbook author tried to or is preferring. So for us, I think Dr. Larson, he prefers the formal definition of a limit, but he also uses the epsilon delta proof. So we'll call it the formal definition of a limit. And I'll also put Cauchy definition in parentheses there because, hey, how about we spell everything correctly? And then we also could write down that this is sometimes called I'm going to write this the epsilon. That's not very good. Epsilon delta proof. And we'll talk about epsilon and delta here in a second, what they are. Okay. So what I want you to think of first is when we define a limit, in Calc AB as first years, you probably have the definition of, as x gets close to c or x approaches c, f of x, the y coordinate approaches some value. We call it L maybe. And so I'm just going to draw that out here, and with my very common function that I draw a lot. So again, if you're new to me, this is the function I use a lot. I know looks a lot better when I draw it on the whiteboard in class, but hey, we go with what we got, right? And I'm going to arbitrarily define some point C along the x-axis here, right here. And as x approaches C, we get that the function approaches the limit L, right? Sometimes that's f of c, sometimes that's not f of c. You can see here I've drawn a nice continuous function, so that would in fact be f of c. Okay, Cauchy hated that. He was like, "What do you mean by x approaches c? What does that look like?" We know what in our head we know what we mean. We say, "Hey, look, yeah, we're just going to pick x values, here or here, right? Here could be x, or here could be x, wherever, and then we're gonna move them in. They're gonna get closer to c, right? They're gonna go that way, or they're gonna go that way. They get closer to c." And Cauchy's like, "Yeah, but mathematically that's not a thing." And so he really wanted us to have to formally define what we mean by getting close or approaching c. The limit as x approaches c of f of x equaling L, it has to mean something. And so what Cauchy wanted to do was just really formally define what do we mean by that. So Cauchy was a real stickler for things, basically, is how it turns out. So what he did was, look, if x is approaching c, what are we really talking about? On the horizontal axis, we're talking about going between these 2 points. So let's define those 2 points. How do you get horizontal distance? That's x minus c. And what he said was, okay, look, if it's x minus c, it doesn't matter which side you're on, that's still the distance if we put it in absolute value. Because now x minus c, even though it was negative, would be positive. That's that distance. And all we mean by approaches then is what? Well, that distance is getting smaller. How small? Well, that horizontal distance is less than some arbitrary value, lowercase delta. That's a delta up there. Okay, that's the lowercase version of delta. You've probably seen the uppercase version of delta a lot. We know that means change in earlier when we talked about slope. we use like delta y over delta x, right? And then we saw how that became delta x, or it became dx, and delta y became dy as we talked about in derivatives. So this is just the lowercase delta. Okay, so that's what we mean. We mean that x is approaching c, this horizontal distance is getting small, and it's always going to be less than delta, where delta is a small number. Yeah, cool. So as long as we pick x's within this range, okay, we're going to have it be small. It's less than whatever that number delta is. And that would make Cauchy say, okay, I understand that, would be Cauchy's response to that. Okay, so x minus c, the horizontal distance, is small. Perfect. And, for us, we could say delta is getting smaller even. All right. Well, what does that mean for the other axes then? Okay. How is f of x then approaching L, right? How is that y coordinate getting closer to L? And what do we mean by that? And well, that's really just a case of, f of x could be anywhere in here, right? Some kind of vertical distance, okay? And in that case, then f of x minus L would be the the vertical distance between the two, right? F of x minus L. And of course, again, if f of x is less than L, we would want to put positive values on it. Okay. And Cauchy said, okay, so then what's happening to that vertical distance is that it's going to be less than some number, and he called it epsilon, where epsilon is also some small number. And so the formal definition of the limit then relies on our ability to define delta and epsilon. Okay? And if we can do that, then Cauchy is satisfied and the formal definition is satisfied and the epsilon delta proof is complete. Okay, so again, I'm going to use a different function just to really highlight this now. In the formal definition, okay, if I have my function, okay, and it's going like this, and I pick an arbitrary point C somewhere on the x-axis. There's C. Then obviously over here, right? Oops, I don't want to do that. I want a straight line. This is what L is going to be. Okay. What we're saying is, let's define a delta so that if we stay within delta units of C, so I'm going to define delta to be, this distance. I'm going to try and match that distance as best I can. Obviously, that's not wide enough, so we're going to go over a little bit. So you can see, right, that this is delta units above. This is delta units below. Then what that does is it defines an interval around L. Get a different color here. Come on. Okay, now this one, they might look they look like they're different sizes, and they are. So we'll just take the bigger one and make that epsilon. Okay. That as long as we pick our values to be within delta units of C, then we will be forced to be within epsilon units of L. That's what Cauchy's definition, that's what the formal definition is all about. It's about figuring out how does delta relate to epsilon. And so what we're going to do here is we're going to run through a quick example. Cauchy's definition then says this. He says, okay, let f, oh, I got to get this tablet figured out, be a function defined on an open interval containing C. And of course, except possibly at C, it doesn't have to be defined there, right? So don't worry about if it doesn't get defined there. And let L be a real number. Okay. Yeah, we don't deal in imaginaries, right? Okay. Then he says this is the limit as x approaches C of f of x equals L means for each epsilon greater than 0, there exists delta greater than 0 such that if, and here we go, our x minus C absolute value is less than delta, and I should say this, right, between 0 and delta, then absolute value of f of x minus L is less than epsilon. So that's what the Cauchy definition actually says. So, it's a lot of verbiage, it's a lot of stuff that really the whole point was just to kind of formally define what do we mean by approaching, right? But Cauchy was a stickler for those kinds of things, and so that's what we mean by approaching. Let's take a look at an example with a very simple limit. So the limit as x approaches 3, and our function is going to be 2x minus 5. Okay, well, we already know what the limit is, right? We know as x approaches 3, we could do direct substitution, we're going to get a limit of 1. Okay, that's not what Cauchy wanted. He wanted you to be able to say, okay, if x approaches 3, what does that mean? It means x minus 3's absolute value is between 0 and some number delta. Then that means there's a connection to epsilon, right? Epsilon is f of x minus L is going to be less than epsilon. Now, our work here is to draw the connection between the two. Okay, somehow we have to connect epsilon and delta in this problem. Well, if you look carefully, you might see over here that 2x minus 5 minus 1 is 2x minus 6. And what do you notice here is factorable? And if I divide both sides by 2, I get the absolute value of x minus 3 is less than epsilon over 2. Okay, but notice in the delta part, I have the absolute value of x minus 3 is less than delta. So let delta equal epsilon over 2. As long as we choose delta to be half of whatever epsilon is, okay, then no matter where we pick x, let me go back a couple slides here. No matter where we pick x, as long as delta is equal to half of epsilon, then we will always be within epsilon units of L. And that's what Cauchy wanted. And I know it seems like a lot for a simple idea, but it really is hard to formally define what it means by approaching. All right, guys, that's it for our video. I know that that may have been a little tough to absorb. Cauchy definition is always tough the first time through. Don't worry, we're going to do some more examples of it in class. And when I see you on Thursday, we'll take a look at some more complicated functions too, because simply doing with linear is kind of an easy one. So thanks, guys. If this video was a little unclear, you can rewatch it. Also, we'll do more examples in class on Thursday. All right, have a great day. Bye, everybody.